W new is equal to W old minus neta slash derivative of dl by dw with respect to d volt, W old. So what are going to update these kind of the equation to get the new neta value for each and every weights. So I will also tell you what is exactly the alpha t minus 1. Alpha t minus 1 is a gradient term. Gradient term. So we are just computing the gradients here itself. But what we are going to compute the gradient in the neta values only. So the gradient of this is just a derivative of dl by with respect to dw. That's it. So I will take the previous timestamp derivative. I'm computing that. So what is this epsilon? Epsilon is going to be represented in this case as in the learning rate concept. It will going to be very helpful to avoid some of the zero values results. What if this gradient is going to be zero? Zero plus zero is zero only, right? In the denominator, if you're going to be get the zeros, that may not be works well to calculate anything situations. So for that, what we are going to do, just avoiding that confusion, avoiding that much of the smoothingness. So what if I have a value corresponding to 0.1 like that, or 0.001 like that, some smoothing approximation with respect to epsilon value. So that's the reason we are taking epsilon value with corresponding some of the gradient to analyze your learning rate. This is come from your same learning rate. We are going to be showcased 0.01 or 0.001, small rounding rate. Even you can take care and compute the derivatives and get the approximation of the new learning rate, and it will go and compute and everything for each and every node according to that. So this is eventually going to be very helpful in the adult delta. But what will happen, the disadvantage with the adult delta is it is very small. What if neta slash is going to be very small, or it's going to be decreased in some of the cases. It takes slower to convergence. That means you cannot get the loss values as much as possible. So alpha, what I mean, neta is going to be increasing, alpha gradient function is going to be decreasing, neta is going to be decreasing, gradient function is going to be increasing. It is vice versa, right? So at the time, what will happen, alpha t minus 1 can become very large as a t is increases. So at that time, it has some of the disadvantage with respect to the neta is going to be decreasing, slower to convergence. So we require faster to convergence, right? We require faster to converge. That's the reason we are using optimizers. We require faster to converge, but what will happen, neta is increasing. That means gradient is increasing, neta is decreasing. Neta is decreasing means slower to convergence. So further we have another model called Adder delta. So the Adder delta concept came into the picture. Instead of computing alpha t minus 1 as a grade square, you can say grade with respect double grading, right, with respect to the neta times and also the efficient weights. So what if I use something different terminology called weighted decay or decay averaging weight kind of the thing, decay average of weights. So if I use this concept too much efficient to understand your neta times to update, so it will looks like this. EDA we can also call it as exponential decay average. So gamma times of EDA. So it will be having the two different timestamps, I would say. Gamma times of EDA t minus 2 plus 1 minus gamma times weight square and t minus 1. So this is somehow very interesting ideas, I can say, exponential of the average weights with respect to the neta values. So if I compute the neta value slash, you can say double slash for that matter. So for the Adder delta perspective, the neta is going to be looks like this: weighted decay of average plus some epsilon value. So we will eventually use weighted decay average EDA for like this formula, so that we will eventually end up with, instead of directly taking to slower to convergence, it will be helpful to faster to convergence. So that is a basic simple ideas with respect to the optimizations, which is which is very popular nowadays. And something is very popular nowadays is Adam. So we eventually learning so many concepts with respect to the optimizations, but those are all disadvantages, I can say. Disadvantage with respect to the optimization concepts with respect to slower to convergence. But Adam is one of the best efficient ways to handle out that fasterness of the convergence. Why it is going to be popular? Still now we have learned so many things, right? Let's connect the dots together in the Adam. So we this learned something called as momentum, and we also learned the idea behind exponential moving average with corresponding to the Ada delta. So yeah, this is very popular in the 2018s and 2016s onwards. So Ada delta we also done with EDA concept, exponential decay averaging kind of the concepts. We also learn Ada grade, some of the different optimizations. What if the Adam is going to be very helpful? The idea is storing simple EDA only going to be stored for the Adam. It's going to be store the Adam for the EDA kind of the exponential weighted decay. But what it will do, it will take, instead of squaring of the gradients, it will take only the taking of the gradient only. Instead of taking at a timestamp of gradient t minus 1, it will take only the gradient of t. And then just tiling out this error, it will be very helpful. At the time, they are using some statistics analysis with respect to the mean and also the variance. So for the mean, we will call it as first order movement. For the variance, we can call it as second order movement. So slightly intercorrelated concepts with respect to the statistics way of analysis with respect to the Adam, which is much more efficient, faster to convergence when compared to the Ada delta. So currently the more popular optimizer is Adam, with the concept of exponential weight decay, and we also use the mean and variance for the first order movement and second order movement. So eventually what will happen, you need to convergence to get the minimal loss results. So if you go and check out how does, yeah, just now we seen, right, the exponential decay averaging kind of this formula. So let's go and check out this notebook so that you will get some idea. I have taken this notebook from some person having the neural network and deep learning concepts with respect to the optimization algorithms. So let's focus on this notebook. Just a second, it's loading. Yeah, so the concept is very simple for the Adam. Let's also try to implement this into the real world example so that we'll get some understanding with gradient descent, stochastic gradient descent, and also the Adam, Ada delta, Ada grade. Which one is going to be more popular and which one going to be efficient to compute the loss results at the end? So that's how we can convey our best, right? At the time we're going to be realizing the CNN, whatever we learned in the PISA kind of the task with respect to the CNN, this is also very helpful, right? We can try to implement by using the Ada delta and RMS prop also the similar kind of the functionalities whatever we learned in the Ada delta, so which is also very popular, I can say RMS prop. So this is one of the optimization algorithm we had. It is having the similar kind of the functionalities we are going to learn in the Ada delta. So yeah, so what will happen eventually if you go down to this notebook, you can see here, yeah, you can see here optimization method, gradient descent with the momentum and Adam. So you can see the accuracy scores consist of the gradient descent is 79% and the momentum having also the same with some oscillations, you can say. And what will happen if I use Adam optimizers with respect to whatever we learn as a first order and also the second order to smooth somehow the curve, I would say. So we already seen the curve going to be looks like this, right? So at the time you smooth some of the curve with respect to at the you can say the lowerness of the value, at the time you reach as a global minima, you will get the good scores. So accuracy is going to be very helpful at the time. At the time you're going to be handled with some of the binary classification settings. So Adam is a much more efficient. You can also see the 79% is much better than. So 94% is much better than the 79%, right? So at the time you realize this is the best results to compute for the Adam.